All right, hello everyone. In this video, let me talk about profit maximization. So in the previous week, we studied the basic optimization theory, where a given function takes the largest or smallest value using the two derivative test. So whenever a function depends on a single variable, we can adopt either first or second test to find out extreme value of the function. So in this video, what I'm going to do, I'm going to apply that derivative test to an economic question that is a profit maximization problem. So this problem pertains to firm's behavior or firm's decision. But when we analyze firm's behavior in the study of microeconomics, we usually assume that firms make a decision so as to maximize profit. And although firms make several decisions in the real world, we are going to focus on two decision problems in this video. In this problem, determination of price. So how to set the price of each commodity. So determination of P. And how many units to be produced. So determination of output is Q. Okay? And we are going to deal with this question in the context of monopoly. So it's just that there is a one supplier producing a certain commodity. There's no competition, no rivals, and no close substitute. So you can think of, say, electricity, right? And this monopolist faces a downward sloping demand function. So if we put the demand function on the domain price and quantity, with the price on the vertical axis and quantity on the horizontal axis, demand function is decreasing like this for quantity. And the way to read this demand function is now we are analyzing firm's behavior. So this quantity stands for quantity produced. Okay. So suppose that this monopolist produces, say, Q1 units. Then, demand function assigns some price to each quantity, say P1. Okay. And the way to read this P1 is this P1 stands for the highest unit price the monopolist can charge on the commodity. So if the price is higher than P1, firm can no longer sell these Q1 units. So this is the highest unit price and the negative association between price and quantity, because there is a negative association that is due to downward sloping demand function. Okay. And the implication of this negative association is easy to understand. So if the firm increases quantity, okay, and then in order to sell this larger quantity than before, firm has to drop the price. Okay? So furthermore, this negative association implies that there is a one-to-one relationship between price and quantity. Okay, so although our question is two-dimensional question, so we have to consider uh, what is the optimal price. So what is the price that maximizes profit, and what is the quantity maximizing profit? Okay, so we have to determine these two variables, but there is a one-to-one relationship between price and quantity due to demand function. So we have to simplify the problem into a unidimensional problem, okay? In the sense that once we determine Q, P is automatically determined by demand function, okay? And vice versa. So I'm going to formulate this problem in terms of quantity, okay? So regarding price as a function of Q, so the market price, the unit price is given by function of Q, that is given by demand function. And along with the total cost function, so this total cost is a cost necessary for producing Q units. So that is originally the function of Q. We can write up the monopolist profit as the difference between revenue and cost. And the revenue is defined as the unit price times quantity produced. But instead of a unit price, we can substitute the demand function. So expressing revenue as a revenue as the product of demand times the demand and quantity produced, right? And then subtracting away cost, we obtain profit function. Okay, so this profit function is just a function of one variable, function of quantity produced. So we can apply the first or second derivative test to find out where this function is maximized. Okay, so our problem is, so we are going to, so we attempt to, so we are going to see where this function is maximized. All right, then denoting the solution to this problem by Q star. So Q star is the profit maximizing quantity. So we first take the derivative of this objective function. So the function we want to maximize with respect to choice variable Q. Okay, so the derivative of the profit is given by, because the profit is given by the difference between two functions. So the derivative consists of two parts. The derivative of the first function, so the derivative of revenue, so R prime, and minus derivative of the second, so C prime. And these two derivatives are important in economics. So they have special names. We call the derivative of revenue marginal revenue. So increment of revenue from selling one more unit of a commodity, and the derivative of cost, marginal cost. So the increment of cost from producing one more unit. All right. And the first other condition, remember the derivative test. For maximum, the derivative should be equal to 0, and the second order derivative must be negative. And for minimum, derivative must be equal to 0, but the second derivative now positive. Okay? So we first take the derivative and set it equal to 0 to find the critical points of this profit function. Okay? But the first other condition boils down to one familiar condition that requires MR be equal to MC. Okay? So at the optimal quantity, a marginal revenue must be equal to marginal cost. Okay? And the intuition is pretty simple. If the marginal revenue is higher than marginal cost, then the firm can increase the profit by producing more. Okay? And if the marginal cost is higher than marginal revenue, then the firm can increase the revenue by decreasing cost. Yeah? So at the optimal quantity, marginal revenue must be equal to marginal cost. All right? But the first condition alone does not necessarily lead us to maximum highest profit, because this is just the first of the condition, necessary condition. Yeah? So in other words, we have to check the sign of the second derivative, so whether second derivative is negative or positive. So here is the graph of profit function. We have two critical points at Q1 and Q3. So at Q1, derivative is equal to 0, so the slope is equal to 0. And at Q3, we have another critical point, so the slope is also equal to 0. But at Q1, so let me first illustrate Q3. So at Q3, we have the highest profit. Yes, the profit function is indeed maximized at this critical point. But at this critical point, the graph of the function is bent downward. In other words, profit function is concave at Q3. Okay? So the second derivative is negative. So from the second derivative test, we can infer that profit is indeed maximized at Q3. Okay? The function attains a local maximum. But at Q1, now the graph is bent upward. So pi is now convex at Q1. So the second derivative is positive. Okay? So at this point, the profit is minimized. The function attains a local minimum. Okay, so this is the way to find optimal quantity using the second derivative test. And if we use the first derivative test, and remember the derivative of profit function was marginal revenue minus marginal cost. That was the derivative. Okay, and then at the optimal quantity, so at the quantity maximizing profit, the derivative, the sign of the derivative must change from positive to negative, right? So the profit function starts increasing. So when quantity is smaller than Q star, the profit function starts increasing. And after hitting the top, the function starts decreasing. Okay? So the profit function attains local max at this Q star. Okay? But there's the positive sign means this quantity MR minus MC be positive. So MR is higher than MC on this interval. So when quantity is smaller than this Q star, but higher than Q star, the inequality is reversed. So now revenue is lower than marginal cost. Okay. So its geometric interpretation is, so here we have marginal revenue curve and a graph of marginal cost. So the marginal cost is given by this U-shaped, so U-shaped graph, and marginal revenue is given by this straight line. It's almost a straight line. Okay? So at the optimal quantity, so around this optimal quantity, so when quantity is smaller than this Q3, so this Q star, marginal revenue should be above marginal cost, like this. Straight line is marginal revenue. Okay, you can see that when Q is smaller than Q3, marginal revenue is above marginal cost. Okay, but when Q is larger than this Q3, this critical point, now marginal cost is above marginal revenue. Right? So at the optimal quantity, marginal revenue must intersect with the marginal cost. The derivative must be equal to 0, but it should intersect from the below. So from below, like this. From above. So marginal revenue must intersect with the marginal cost from above at the optimal quantity. And we have another intersection at Q1, but difference is now marginal revenue intersect with the marginal cost from below. Okay? So at this point, profit is minimized rather than maximized. All right, so with this background in hand, let's do one example. So in this example, market demand is given by linear function, and total cost is given by cubic equation. Okay? And we want to find the profit maximizing quantity. So let me first write down the profit function. So express profit as a function of a quantity. So pi is revenue minus cost. But revenue is P times quantity, unit price times quantity produced, and minus cost. Okay, but instead of P, we can substitute market demand function. Okay? So 100 minus Q times Q minus cost okay, and then we take the derivative, find the critical points of this function. So 100 minus 2Q minus Q squared minus 14Q plus 111. Okay? And set this equal to 0. right? So we come up with one quadratic equation, um, and if we arrange this equation, minus q squared plus 12q and minus 11, and this equation is factorable. So this expression is factorable. So I can factor out, say, q minus 1 and left with q minus 11. And I have one more negative sign in front because the leading coefficient is negative. Yeah? So without the help of quadratic formula, I can solve out this quadratic equation for q, and I obtain two critical points. So 1 and 11. Yeah? So we have two candidates for optimal quantity, so where profit is maximized. But now let me use the second derivative test. So, because this is the first derivative, and if I take the derivative one more time, then I obtain pi double prime, that is minus 2q plus 12. Okay, and our candidates were 1 or 11. So there are two critical points, 1 and 11. Okay, and at 1, so if I substitute 1 for q, pi double prime is positive. So profit function is convex at the first critical point. Okay, so I can infer that from the second derivative test, profit is, yeah, so it attains a local minimum at that point. All right, and then if we plug in 11 for q, then now pi double prime is a negative, so pi is concave at 11, so attains local max. Right? But this is just a relative maximum. We are looking for global maximum. Then how do you demonstrate that this 11 is indeed, so the profit is maximized, globally maximized at this quantity. So now we have to examine the sign of the derivative. So remember, this is the first order derivative. Okay? So pi prime was negative q squared plus 12q minus 11. And if you drop, so with this interval for q, we have two solutions, 1 and 11. Okay, so we have 2 points where the sign of the derivative changes. Okay, and you can easily check that the sign of the derivative is negative when q is lower than 1, and between 1 and 11, the sign is positive. So the sign of this expression is positive. And if for q higher than 11, the derivative is negative. Okay, so the graph of function, the graph of profit looks like this. It is initially decreasing, and after hitting the minimum, it starts increasing. And after hitting the local max at 11, it starts decreasing like this. All right, and we want to demonstrate profit is maximized at 11. Okay, and we don't have to worry about this region. There's no hope that we have a global max at some quantity higher than 11, right? Because the function is continuously decreasing. Okay, and then we don't have to worry about this region. So the only chance that function has a global max at other point is the left-hand point, because the quantity is a positive is a positive variable, so it has a left-hand. So quantity is defined on the interval between 0 and infinity. Okay, so the left-hand point is the y-axis. Okay? So we have to compare the profit at 0 and at 11. Okay, but going back to profit function, if we plug in 50 for Q, if we plug in 0 for Q, then we obtain negative 50. So this negative 50 can be thought of as a fixed cost or sunk cost. Although the firm shut down, the firm is shut down, it incurs cost as much as 50. That must be a fixed cost. Okay? So the profit amounts to negative 50 at 0, but at 11, so I'm not going to compute the exact profit, but you can easily check that profit is positive. Yeah? So if you substitute 11 for Q, then profit will be positive. Okay? So that shows us, so that proves that profit is indeed maximized at 11, globally maximized at 11. Yeah? So profit attains a global maximum at this quantity. Right? So in order to maximize profit, the firm produces 11 units. So Q star turns out to be 11. And what is the optimal price? That is from the demand function, 89. 100 minus 11. Okay. So in order to maximize profit, the firm produces 11 units and sell each unit at the price of $89. Okay, so that's the way to determine price, optimal price, and optimal quantity using the derivative test. All right. And I prepared one more application regarding convexity and concavity. So it has a nice application to risk attitude. So if the utility function is concave, we say the decision maker is risk averse. And in case of a convex, we say that decision maker is risk loving. But this is overlapped with intermediate microeconomics. So let me skip this application in this video. Okay. So in the next video, we are going to start with chapter 10, some transcendental functions. Hope you guys enjoyed this video, and I'll see you guys in the next one.